Hello, welcome everybody. Thank you very much for joining to our first 2021 webinar. Happy New Year all. Today we are very happy to have with us Dr. Alexander KEIL, who is an assistant professor in the Department of Epidemiology at UNC. And today's workshop is on causal inference for exposure to mixtures. And with that, Alex, the floor is all yours. Thank you.
Great, thank you, Nancy. Please let me know if at any point you cannot hear me, and questions are welcome along the way. You can either unmute and interrupt, or Marianthi has been kind enough to monitor the chat, so you can just enter something in chat if you'd rather not interrupt. But as she said, I'm Alex KEIL from UNC, and this was originally intended to be a pre-conference workshop, transition to an ISEE sponsored webinar that was scheduled a while ago. And then we had to do a last minute change when my daughter was exposed to SARS-CoV-2 via her daycare. So I appreciate everyone's flexibility in dealing with that audible. So just a reminder, if you are unmuted, go ahead and mute yourself. Otherwise, we'll get going. So it seems a little odd to not acknowledge the world at large around us. I think, you know, the first scheduled time for this webinar was canceled by the pandemic, and you know, I thought there could possibly be nothing worse that would come up during the same time, but lo and behold, we have. So yesterday, armed insurrectionists at the suggestion of the sitting president of the US broke through police barricades and entered the US Capitol building in Washington, DC. The riot was timed to coincide with the proceedings at which the peaceful transfer of executive power was to occur. As of now, 14 DC Metropolitan Police officers were injured during the riot. 4 individuals died, including one as a result of a gunshot wound inside of a Capitol building. Multiple pipe bombs and Molotov cocktails were found in the subsequent cleanup around the area. Metropolitan police officers were shown on camera explicitly allowing some rioters into the Capitol and assisting rioters as they left the building without arresting them. Last I heard, there have been 15 people arrested. The sitting US president and members of the US legislative branch continue to openly assert against all evidence that the incoming US president was elected fraudulently, and are openly advocating for selective disenfranchisement of citizens of their country and denying, again against evidence, the role of their supporters in the riots. So I applaud all of you for showing up today. You know, I always love to teach, and I always love to have a chance to present my research. But now is an extremely challenging time to be a consumer and a learner of those things. So I really appreciate all of you, and you know, certainly if you need to take a break, I will not be offended at any point during this time. So just a sort of 2,000-yard view of this talk. It'll start easy, it'll get a little more difficult, and then it'll get easier. There are materials for this. Originally, this was slated to be a workshop. So there was sort of some code that we could follow along with. And I've had to pull an audible a little bit on the materials that I'm presenting, because this, you know, it doesn't really work well in the webinar format. But if you just go to my GitHub page, which is AlexPKeil1 at GitHub, you can, let's see, I can't do this while I'm sharing this part of my screen. So let me switch over. So go to repositories and then 2020 ISEE Causal, and you can download the whole thing just as a zip file by clicking here. And this will have the slides, and then I've included just one bit of R code, some data that you can use, and these are simulated data, so there's nothing confidential here. And then just the output that'll appear at various points in the talk. So you can go there at your leisure. You don't need to go there now. There's nothing that I'll be asking of you during my talk today. So just taking a broad view of causal inference in mixtures, one major barrier to causal inference in mixtures, and I think this is probably the major barrier for students coming up, is that none of the simple textbook examples apply. So if you don't have an advisor that's working on causal inference in mixtures, it's really hard to come across mixture specific examples that are useful for causal inference. So today we'll create a map from things you may know, and I call this textbook causality, and I'll review that quite extensively actually, to things that I hope you can become more comfortable with, and that's causality in mixtures. So this is taking sort of the things that are taught in EPI 101 through the end of graduate school EPI in terms of causality, so things like DAGs, some of the causal inference assumptions. We'll be taking those and then mapping them onto the context of exposure mixtures. And you've all heard this already, but this session will be recorded and you can access the materials. So I will move fast, but please do ask questions if anything comes up in the meantime. So the scope today is restricted in the sense that I'm interested in a very specific question that might be asked of mixtures data. And here I'll just ask you to use your own sort of definition of mixtures data. There are definitions out there that it has to be 3 or more exposures that occur in the same time and space. And that's what I use in the examples going forward, but mixtures can mean a lot of things. Generally, just what it means is you've got several exposures that you're interested in at the same time, and they're probably correlated. So the question I'm interested in most broadly is what would be the health impact on some health outcome if we could modify some or all of the exposures in the mixture. So this is a somewhat broad view of what I'm interested in, but this rules out a few questions that might be of interest in mixtures. I think you've probably all seen Marianti's diagram on this, but there's lots of questions, about classifying exposures or categorizing exposures, clustering exposures, all sorts of things that you can do with mixtures data that aren't necessarily fitting in the causal inference framework that I'm talking about today. So I sort of think of this as the most important question, and I often talk that way. This isn't offense to anybody else's research track. I'm just enthusiastic about my own. So broadly, you could call this endeavor causal effect estimation. I like that label, but it tends to be lumped under causal inference. So I'll use that throughout. But really what we're talking about is estimating effects of exposures. And that's what I mean by causal inference. So if you have to, scoot out in the next 2 minutes, this is sort of a 50,000 yard view of the rest of the talk. Causal inference combines sometimes unverifiable assumptions and past observations to sharpen knowledge about how we can change the future or what we should have done differently in the past. Causal inference, and I emphasize the word not here, is not the application of special methods that distinguish causation from correlation in a given data set. The tools of causal inference, or the statistical methods that came out of the field of causal inference, are effective for evaluating new methods. And specifically, thinking back to the study question, do these methods answer the question that I want to ask? And I'll go through some examples today of how we go about answering the questions we actually want to ask. One might be curious about how I'm going to define cause. There's been a lot of different definitions of cause in the literature throughout history, dating back to a long time ago, and sort of it's a little bit disingenuous to say that causal inference is really a recent thing, because people have been making causal inferences since they could make any inferences at all. So we'll sort of narrow down on what I mean when I say cause, because that does have implications for the scope of causal inference in epidemiology. So many definitions that have been given throughout history, or at least common uses of them, are incomplete, ambiguous, or too restrictive. I've got footnotes sort of throughout. I won't really go over those, but you are more than welcome to ask questions about those if you like. So we can come up with a useful definition of a cause that's really rooted in epidemiology, which is where I'm rooted, which is that a goal of improving and not just observing public health leads to a policy definition of a cause. And when I say the word policy, I don't necessarily mean public policy. Policy is used to refer to some function that takes as input a current state and outputs an action. So given that we've measured some exposure, what do we do with that? What action do we take? And that's really the policy definition of a cause is taking some state, changing it, and seeing the difference between those two. If you do see a difference, then you've potentially identified a cause. If you don't see a difference, then there is no cause. And this is sort of a vague definition on purpose, but really the point is that a cause in this public health context is really nearly always about comparing two different states, exposed or unexposed, high exposure versus low exposure, exposure at some specific amount versus exposure at some other specific amount, exposure to sort of things as they are versus exposure to things as you would want them to be, if we could eliminate some source of exposure. But generally, when I think about causal inference, I think about comparing two different states. And this goes a little bit against the grain in terms of mixtures, because a lot of times in mixtures, what ends up being estimated are things like dose response functions, where it's not a comparison necessarily of two states. And we can map it onto there, but it's thinking more of a continuum of policies or sort of a function that where we input an exposure and we get an outcome. So you'll see this a lot come up throughout, that most of the effect estimates that are coming out of causal inference really are sort of these comparisons that we see a lot in epidemiology, which is exposed versus unexposed, but the definition of exposed and unexposed will vary by the context. We can define a cause using policy by saying exposure causes an outcome if some manipulation of the exposure via an intervention would change the outcome. Again, this is very generic, and this is just getting to the idea that sometimes we have exposures that we actually don't think are causes of the outcome. And this gives us a useful way of thinking about what we can say when we say, or what we mean when we say that an exposure does not cause an outcome. What that generally means is that, sorry, I forgot to hit my timer. What that generally means is that no matter how we change the exposure, if we could manipulate it, it wouldn't change our outcome of interest. And that's sort of our null hypothesis. And if it does change, even if it doesn't change every time we change exposure, but say, it changes our health outcome at high levels of the exposure, but maybe not at low levels of exposure, we would still call that a cause, which we're not going to be able to identify in every study. But this is taking sort of a broader view of what we mean by cause. Causal effects contrast one policy with another. Causal effect estimation allows optimal policy choices. And what I mean here is, again, sort of contrasting with the mixtures literature, where we're focused on oftentimes exposure responses, but finding sort of an ideal amount of exposure for a particular health outcome. And that's a lot of times in environmental epi, we think the ideal amount of a lot of the exposures we study is 0. But if you think of exposures that could be healthy for you, thinking of some dietary exposures, for example, the optimal policy or the optimal mixture that we might find is not always one where we've reduced every constituent to 0. And so causal inference or causal effect estimation is really a nice way to sort of hone on these pieces where there's a nice public health relevance for everything that we estimate, and not just something like an exposure response parameter where you may or may not need a PhD to just understand what those are. Epidemiologic causal inference specifically is about improving decisions for groups in context. And what I mean by that is, we can make decisions based on exposure response curves. We can do something like null hypothesis testing, where we come up with sort of this vague intuition that some exposure is bad for some specific outcome, And so we make a decision to possibly ban that exposure or reduce it. But we don't necessarily know what the impact of that decision is going to be just based on the exposure response curve. That's not something that comes out of epidemiology too often. So what epidemiologic causal inference is focused on is thinking about, what is sort of the decision that we're making and what would be the implications of that versus taking a dose response parameter and making a decision that's completely sort of abstracted from the thing that we actually estimated. And when I say for groups in context, I mean, causal inference isn't about making individual decisions for the most part. There are parts of causal inference that are focused that way, but that's not what causal inference is in general. It's focused on making decisions for groups. So those decisions may lead to bad outcomes for some individuals and good outcomes for other individuals, but on average, the goal of causal inference is to improve the average outcome in a group. And the context there is really important because contextualization in epidemiology, we've come to this idea of the target population recently, where really we want to make our inference with respect to specific populations. And that's what I mean by context, is we've got specific populations, we've got study populations, we've got target populations that may be outside of those study populations. We may have subgroups of our study population that have particular relevance to a question that we're interested in. For example, if we're going to do something like stratifying by race to examine effect measure modification, epidemiologic causal inference really gives us a nice set of tools for thinking about effect measure modification that allows us to make good decisions based on those kind of stratified estimates. And I'll get into some examples later of exactly what I mean by that. So throughout, I'll use this motivating example of coal-fired power plants and cognitive development. And I won't spend a lot of time on the subject matter here, mostly because this is a simulated data set. And so the subject matter sort of is what I say it is, but we can think of this as being sort of an approximation of some reality. So burning coal for energy produces many byproducts, including a mixture of air toxics. Some of these have known detrimental effects on early life cognitive outcomes. One example of how we know this is that closure of coal-fired power plants has been previously associated with improvements in cognitive outcomes. So mostly so I can share the data, but also because it makes this example focused on mixtures and a little bit cleaner, I performed a simulation study of exposure to coal-fired power plant emissions and mental development index in a group of simulated kids. So the data set that I'll be using in all of these analyses, and this is up on the GitHub site, is it comprises 2020 3-year-olds. And each of them have measured exposures associated with them. So that exposure is going to be the annual mean residential air exposure measured in micrograms per cubic meter. There are 2 potential confounders included in the data set, urbanicity and Black and non-Black race. And we'll call that self-reported, even though it's a simulated self-report. And both of these are considered potential confounders here. Urbanicity will have a direct effect on proximity to coal-fired power plant. And then, possibly associations with mental development index through some unmeasured common cause. So this is what this double-headed dashed arrow means, is just that there's some unmeasured set of things here that we think, affect both urbanicity as well as mental development index. This could be things like other exposures that are associated with being close to the center of an urban area. And then the same thing with Black race here, where we're not supposing any direct effect on either of these things, but for historical reasons, race is going to be associated with both the outcome and the exposure. So it's a potential confounder. And then we've got 3 potential exposures of interest: arsenic, beryllium, and cadmium. Partly these were chosen so that I could have A, B, and C as the letters throughout, but these are indeed 3 exposures that do come from coal-fired power plants. So again, this is a simplified example, but we've got a couple key features that will make this helpful and extensible. That we've got several exposures. These are all continuous. We've got a continuous outcome, and we've got a couple of potential confounders. So we can really explore a lot of different concepts in causality this way. So just starting out, it's always good to think of the causal questions of interest. And I think of the causal questions of interest as a good starting point, even before you collect data, because oftentimes these can inform what we might do. And so in the causal world, the questions aren't oriented around dose responses or necessarily hypothesis tests or anything like that. But they're framed in terms of, again, these policy changes or policy causes. So we could think of a causal independent exposure response, not something that's often done in causal inference, but we could do it, is how the population average mental development index changes as we increase arsenic, but we hold other exposures constant. Second one is a causal joint exposure response. So how does the population average MDI change as we increase all exposure by the same amount? Causal attributable difference, and this is akin to an attributable fraction if you're thinking about binary outcomes, but how does the population average MDI change after we eliminate all or some exposures? And finally, a generalization of the attributable difference is what's been come to known as the generalized impact fraction, or I call it the impact difference because we've got a continuous outcome. But how does the population average MDI change after we reduce all or some exposures by some policy relevant amount? And again, this is it's a comparison of two states, sort of the natural course, where we're thinking of not reducing exposures at all. And then we've got a comparison group, which is going to be where we've reduced all or some exposures by some policy relevant amount. I like to think of these as the questions you might ask if you could design a really unethical randomized controlled trial to assess the effects of mixtures. These are aspirational questions. So the nice thing about causal inference is that it allows us to ask questions with answers that make sense to people who don't know what regression is, but we don't necessarily have to sacrifice rigor, either in interpreting our results or in producing results that are interpretable. And I always encourage students to ask causal questions, at the start of a study, because it helps focus and choose methods even when causality is hopeless. So even when we don't meet causal assumptions, it's always useful to frame your study question in terms of a target trial within a target population. And you may not end up getting there, but it's always nice to shoot for something that is interpretable and that you could express to your grandparents without them being too confused. So I'll spend a fair amount of time reviewing some foundational concepts and hopefully deepening some of the understanding of these particular things. I'll talk about counterfactuals, potential outcomes, and consistency, and then some of the causal identification assumptions or causal identification conditions. And you may or may not have had these in your schooling up till this point. Hopefully you've at least been introduced to these ideas a little bit. We'll get a little bit technical with some of these ideas. This is where the talk gets a little bit more difficult in terms of notation, but I'll talk you through it as much as I can. So every causal inference talk always has this notation slide. I've simplified mine as much as possible. So this is for historical reasons. I've got a univariate exposure treatment denoted as this letter A. And so A is the random variable, and then we've got realized values that take on these lowercase variable, this lowercase letter. And for now, because I'm going through sort of the textbook examples, we'll stick with a binary exposure. So there's actually an interesting etiologic root for this using A. A originally started as meaning arsenic. So Jamie Robbins wrote a paper in 1986 that you could think of as really kicking off causal inference within epidemiology, where he used this notation, A is the exposure, because he was studying workplace arsenic exposure. Traditionally, we'll use the univariate outcome Y. So Y will later come to stand for MDI, but this could be, it could be binary, it could be continuous. But the thing is that it's univariate, meaning it measures only one thing. And that's the world we'll live in today, and avoid multivariate outcomes. I will denote confounders as W, and non-confounding covariates as V. These will sort of show up rarely, but they will be there. This might be something like you think you have something that's not a confounder, but maybe it's an effect measure modifier. And so you might adjust for these things, or it may be something that's necessary for transporting a causal effect from one population to another. That again is not a confounder, but it's something that's necessary for transport. As little as possible, I'll use this little I subscript for individuals. And the great simplification, the biggest simplification of this entire 2-hour period is that all concepts will be introduced for time-fixed data. In my experience, most of the field of mixtures is still focused on time-fixed data. The nice thing about causal inference is that it generalizes to time-varying data. It's complicated, but it still gives you simple inference. But just understand that if everything looks really easy today, this is really why. It's because we've avoided some of the complications that happen when we introduce time. So you may have seen a definition of counterfactuals before. I refer to counterfactuals as the policies that are counterfactual for each individual. So we've got a little fake data set where I've indexed ID. I've got some W confounder. It's continuous. Some exposure A, yes or no. So it's binary. Some outcome, yes or no. And so we've got factual individuals. So this would be something we would actually see in our data set. And another factual individual here. And then we've got counterfactual individuals. And I emphasize the term counterfactual individual or counterfactual policy, just to note that it is this row that is counterfactual and it's not an outcome that is counterfactual. So this is just a sort of newly found pet peeve of causal inference folks everywhere, is the confusion between counterfactuals and potential outcomes. So just to avoid any confusion, counterfactual refers to this entire row. It's the exposure that may have occurred counter to fact. So we observe this person being exposed to A. The counterfactual for that person is that this person was unexposed to A. And there's also a counterfactual here where A is set to this exposure. So this is to distinguish another kind of important concept that Judea-Pearl talks about a lot. So we can think about observing A, which is what we've done here in this factual individual, or we can think about setting A, or Judea-Pearl uses the term doing A. And this is a counterfactual too, because this is, we haven't actually been able to make this manipulation in reality. So we'll call this this individual or this doppelganger also a counterfactual, even though they are otherwise identical to the factual person in the data set. Oops. So to distinguish from what is sometimes called counterfactuals, to refer to an outcome that may or may not be observed, I'll use the term potential outcome, and I'll superscript our outcome variable with A. So this is the value of the outcome Y that we would have observed had exposure been set to some value A. So these potential outcomes are the outcomes of our doppelganger individuals had we been able to set exposure to some value A. All of this is done without assumptions at this point. We're just defining terms. So causal inference really is something that happens according to these counterfactual worlds. So we think of a counterfactual comparison of exposed versus unexposed is really these things we don't even observe. And if we really want to make causal inference, we compare these two things we observe. This is problematic, obviously, because we can't measure those things, so we need to make assumptions. And the first assumption, sometimes called an axiom, is called causal consistency. And this is the way that we link our factual world or the measurements we make to the counterfactual observations, which are those other rows in the table. So it's a way to link person ID1 who was in fact exposed with the counterfactual person ID1 who had their exposure set to exposed. So causal consistency just means that if we observe A to be little a, then we can make this substitution where our potential outcome is replaced by the observed outcome. So this means that we've measured at least some of the potential outcomes, and we have some hope of making causal inferences that way. And generally what consistency means is that we would expect an individual to have identical outcomes if we set A via policy or if we observed A equals A. There's actually another buried assumption here. This assumption actually requires what's called SUTVA, which incorporates one other assumption that we'll get into later. But if you ever see this term SUTVA or the stable unit treatment value assumption, this is sort of an historical term from Donald Rubin that still gets used as a way to link the counterfactual and factual worlds. So given causal consistency, we can fill in some of this table. So now we've linked the factual with the counterfactual, and we could say that because we observe this person to have A equals yes exposed, in the counterfactual world where we set A to be yes, we can just fill in or impute that particular potential outcome. So here we've created a link with some of these counterfactual individuals. Here's another way that you may see this laid out. This was actually done by Don Rubin in 1974, who before Jamie Robbins really brought the idea of potential outcomes back into statistics. But this is just a different way to frame the table where instead of having an entire counterfactual individual, we're only including the potential outcomes as different rows. So this brings up the problem that we still have even after making causal consistency assumption or axiom, is that really if we want to think about causal effects happen on the individual level. So it's a comparison of you had you been exposed versus you had you been unexposed. And this is missing. We don't know this because even though we can link your counterfactual world to your observed world for the counterfactual where you set A equal to yes, there's still this counterfactual where you were unexposed, and we don't know what to fill in here because in fact in this world you were exposed. So we need to make more assumptions in order to make any progress. This is often given as sort of the causal effect or the individual causal effect. We could also use ratios. There's nothing really special about this additive difference. So even with causal consistency, we have some potential outcomes missing. This is often called the fundamental problem of causal inference. And I'll use the term fundamental problem a few times today. So we need more assumptions. Because we refer to the idea that we can't get individual causal effects as the fundamental problem of causal inference, we should sort of cue into that term that it is fundamental. In fact, the idea is really that without making much stronger assumptions, we can't actually get individual causal effects sort of at all. We might think of longitudinal designs where we could sort of get there, but sort of the basic vanilla causal inference, we're sort of operating under this assumption that we can never actually estimate individual causal effects. But using a sufficient set of assumptions, we can estimate average potential outcomes, which would mean this is where we can get to average causal effects. So we could estimate the population average, had everybody been exposed versus the population average had everybody been unexposed. So even if we're not filling in individual causal effects, we can still get to these population effects. And this again is emphasizing the point made earlier. The causal inference is really about populations and not necessarily about individuals. These are some definitions that come up. They're not really important other than to say, sometimes we will condition on things. So here we're conditioning on a confounder. Not all causal inferences are going to be marginal or over the whole population. And we can actually conceptualize a causal dose response as really just being a function of these. And this gets into marginal structural models. But for the most part, the bread and butter of causal inference is really this population or sample average causal effect, where we have this nice little thing where the average of the individual causal effects is equal to the average of the potential outcome under one exposure versus minus the average of the potential outcome under the other exposure. And this is this may not seem at all interesting at this point, but this is actually a trick that allows us to do quite a bit. We won't spend a lot of time on this, but just want to emphasize that everything we're doing is presupposing a specific population, often referred to as the target population. The target population may or may not be the study population, but when we're thinking about causal effects, it's always reference to a specific population. We're not trying to identify these sort of universal quantities. That's sort of looked upon as that doesn't really exist. There are, potentially units that are generalizable from one population to another, but when we think of generalizing overall in terms of, these marginal or average causal effects, really the target population becomes very important to contextualize the results. And again, I won't spend too much time on this, but this is something you'll see in causal inferences, that there's a big emphasis on defining your target population. So formally generalizing these causal effects relies on having this conditional average causal effect. So that was the causal effect where, I condition on either a confounder or some of these other variables. And again, this is just to emphasize that if you're making inference in your study population, it doesn't always apply to the target population that you think it is. So we wouldn't say something is generalizable yes or no, but we would say it's generalizable to a specific population or transportable to a specific population. So just to keep hammering away at this point, the average causal effect really is vacuous without first defining the target population. It's not the study population often, because oftentimes we really select study populations for statistical reasons. But nonetheless, today we'll stick mostly with just the study population. So we'll sort of drop this thread from this point on. So returning to this main thread, causal consistency alone is not sufficient to license the estimation of average causal effects. And license is a key word here. So again, emphasizing causal inference is not about having a method where you throw in some data, you crank through, you get results, and all of a sudden those are causal. Really what you need to think of is finding what you can do to license the estimation of average causal effects. The methods of causal inference themselves are often just statistical methods, but we need to think of the conditions that allow us to make causal effects, and it's not just fitting a specific model. So let's consider a scenario where A is vaccination and Y is SARS-CoV-2 infection. So A would be obviously the coronavirus vaccine. Your infection, if not vaccinated, doesn't just depend on your vaccination status, but it also depends on the vaccination status of your neighbor. And this turns out to be a little bit problematic. So if your potential outcome depends on others' exposure, the potential outcome would have to be denoted by your exposure as well as everyone else's exposure. And so you get to this just really awful looking way to express potential outcomes where you've got your own exposure plus everybody else's exposure. And that sort of breaks the math, it makes everything ugly. So causal inference in the context of infectious disease is sometimes challenging because of this. Michael Hudgens at UNC has done a lot of work on this. So there's certainly ways forward when you have what we call interference, but it definitely makes things harder. So we'll pretend as though interference doesn't exist at this point, and for a lot of environmental mixtures contexts, really that's a valid assumption. So this is often referred to as the no interference assumption, just that your potential outcome depends only on your exposure and not those of your neighbors. This is a subject matter call. So if you're in, again, the realm of infectious disease, this might be violated, but otherwise, in a lot of cases, you might not think it is. You can end up with problems like clustering. So if you're doing a cluster randomized trial, you may have some evidence that you do have interference among units, but for the most part, causal inference sort of operates in this world outside of no interference. So causal consistency and no interference give us what I refer to as the observed potential outcome. So that was the table I linked to before, where you can just fill in, one of the potential outcomes based on the exposure you happen to observe. But causal inference also requires us to know something about the potential outcomes under the counterfactual exposures or policies as well, or the exposures and policies that don't happen to coincide with the observed data, the counterfactual exposures policies that don't coincide with the observed data. So your counterfactual had you been unexposed, given that you were exposed. It's those potential outcomes where we can't just fill in something from your existing outcome. The link between these counterfactual policies and the observed data comes by conditional exchangeability. And this is given by this sort of, not very friendly looking equation, but this is just saying that your potential outcome is independent of, that's what this little upside down pi is. It's independent of your observed exposure given your covariates. This is sometimes called conditional randomization, because if you think of this like a randomized study, what this is really saying is that the future is sort of independent of which exposure you got. It's not saying necessarily that your exposure will not affect your observed outcome, but it's that your potential outcomes don't change whether or not, or don't differ based on whether or not you actually had been exposed or not. So you could think of this like balance in a randomized clinical trial where we're not assigning exposure based on, some underlying health status. And we generalize this to being conditional on W. So we could think of this as a stratified random sample in a randomized control trial. But this is really the assumption that's key for taking observational data and making causal inferences, is that we have to identify some set of variables W. And in this case, it's sufficient if W is the set of variables that are confounders and sources of selection bias. If we can identify those things that make this true, then we can make causal inferences. And this actually gives us sort of a roundabout way to define confounders. It's all the things that we need to throw in on the right-hand side of this bar in order to say that our exposure is effectively randomized in strata of W. So this doesn't give us individual potential outcomes. Again, this is the fundamental problem of causal inference. But we can impute average potential outcomes via this equality. So because our observed exposure is now independent of the counterfactual, if we're thinking about or potential outcomes, there you go. If we're thinking about taking the average potential outcome, this is independent of our observed exposure. So we could throw in any level of exposure we want here because these two things are independent. This is just sort of a consequence of how probability works. And so using this, we can impute our expected outcome under data that we haven't seen. So we're interested in the potential outcome under A being little a, given that we observe someone to have A not equal little a. And all we do to estimate that in the data is fill in the same thing, but now among those with A equals A. So this isn't quite enough to give us the ability to do causal inferences. But again, these are things that we've already filled in using causal consistency and the no interference assumption. So now we've got everything we need. We've got data that we've already imputed, and we can impute the last little bit of data almost. So one thing to note about this is that you can call this a conditional causal effect. This would just be causal effect. Sometimes this is referred to as causal effect, I should say, by Udea Pearl, even though there's no contrasting condition. But really, this is the average potential outcome. So you can think of the conditional average potential outcome. This really only makes sense if it's possible to observe this combination. So A equals A, little a, W equals little w. Otherwise, we're conditioning on something that doesn't really exist. And so we get what we would call an ill-defined question. One way to rewrite the idea that this has to exist is the positivity assumption. So you may have seen it in this form where we say the probability that A takes on this specific value of A under the policy A equals little a, given W equals little w, that probability has to be greater than 0. It also has to be less than 1. So this is positivity, or the assumption of positivity is sort of the last essential or sufficient assumption that we need to make in order to make causal inferences. So just as an aside, positivity means that for a given policy little a, so set exposure to be little a, that value of the exposure must be possible at all joint levels of confounders. There's a related condition. It's sometimes called stochastic non-positivity. I prefer the term sparsity because they really are different issues. Sparsity can occur when this policy is possible. So there's nothing that says we can't do this in the data, but it's just not observed in the data. So this would be common in small data sets. You can think of non-positivity as being always biased, and our causal question may be ill-posed. So one example of a violation of positivity would be studying the effect of hysterectomies among people born without a uterus. It would be impossible to set hysterectomy equal to 1 among someone with a uterus, simply because that's not really a defined thing. So that's non-positivity. Sparsity also leads to bias, so it's still a problem, but we can often reduce or eliminate bias with either more data or a model. And that's the key distinction. If non-positivity is a problem, you have to change the question because you're probably asking a bad question, or at least a question that is unanswerable. But with sparsity, there's at least some hope that through study design or clever modeling that you may overcome that issue. These 3 things, no interference, conditional exchangeability, and positivity, are often known as the causal identification conditions or causal assumptions because they are sufficient to identify a causal effect from observed data. And by identify, that really just means like you could do a tabular analysis and you could see these things just from frequency data or frequency summaries of the data. And it's not necessarily something where you would need to fit a model. in a perfectly run randomized trial, and the word perfectly there does a lot of work, these conditions will hold by design. In observational studies, we really need to rely on subject matter knowledge to judge how well these assumptions are met. And this is, again, this is doing a lot of work too. This is really the hard work of causal inference is the subject matter knowledge. The methods are what the methods are, but if you don't have the subject matter knowledge, you really can't make causal inference. Just as an aside, conditional exchangeability, that sort of ugly term, this matches up with things you may be more familiar with, which would be DAGs. So here's just a sort of sub-example of our previous example, where instead of using the generic terms, I've got MDI, our outcome under no exposure, no arsenic, is independent of your observed arsenic exposure in some strata of one of the confounders. And for this simple DAG, it's the only confounder. So these two things, they're not equivalent, but they're consistent with each other, meaning we would do the same analysis under this DAG as if this was the exchangeability assumption that we knew. The reason why both of these things are useful is that the DAG is great for picking the variables we need to adjust for. The exchangeability assumption is great for doing kind of the underlying math of causal inference. And you'll see a little bit of that, but not too much. And this is just where another place where the subject matter comes in is you need it to design a DAG in order for this assumption really to hold. So together, the causal identification conditions give us the following, and this is the solid link between potential outcomes and observed outcomes, or counterfactuals and our observed data, is that given that all those things exist, we can take something we can actually estimate in the data and tie that back to a causal quantity. So the expected value of y given a is equal to little a, w is equal to little w, this can sometimes seem abstract, but really this is what you get out of a regression model if you fit a regression model where your y is your outcome and you enter a and w in as exposures. Now, there's parametric assumptions laid on top of that, but really you can sort of mentally substitute this for a regression model. And that makes causal inference make a lot more sense, because what it means is what we've been doing all along is causal inference. We've been fitting regression models for forever, provided the confounders were correct, the model was okay. We've already been making causal inferences. It's sometimes given as a criticism of the field of causal inference that really this is what we came down to, is that we've been doing the right thing all along. But the important thing here is that we now know exactly the conditions that need to hold in order for this to estimate a causal effect. Whereas we've been kind of working in the dark for a long time before that. That's just restating what I said. So I'm going to spend the rest of the time digging a little bit more into the coal-fired power plant example. I sort of introduced it and then ran away from it. And this is really where the textbook concepts that we've already discussed, where those meet up with mixtures data. So it's taking this world where we've got binary exposures, probably binary outcomes, at least when we're thinking, or binary confounders when we're thinking about exchangeability, and sort of doing things non-parametrically, and moving into this world where we've got continuous exposures and we've got more than one exposure of interest. So causal inference has been, sort of very focused on what is the effect of a single treatment, and that really is sort of hard to extend naturally to the mixture scenario, where we've got a lot of things that are of interest. In some cases, if you're thinking about independent effects, there's nothing special about mixtures. It just means maybe we have more confounders and we've got some statistical issues. But for some of the other questions of mixtures, there's really not necessarily a straightforward extension where we sort of have this bridge into the mixtures world from causal inference. So my hope is that this section sort of ties that loop a little bit and gives you some tools for, at the very least, thinking about causal inference in the context of mixture, but then also get into some specific statistical methods that have come out of causal inference that can be used with mixtures data. So we'll get into sort of why the textbook examples fail mixtures. There's really, sort of two obvious reasons why. And then I'll discuss these. These are often called like the methods of causal inference. Really, that's kind of an overstatement because inverse probability weighting and g-computation really are, it's more like causal inference methods in the school of Jamie Robbins. So there's a whole other world of causal inference that involves things like propensity score matching or instrumental variables. I'm not going to touch on any of those at all. I think the extension of those pieces to mixtures is maybe a little bit more tricky. You could think of maybe the Mendelian randomization as being some way to bring in genomic mixtures or something like that. But really, for the most part, for a lot of the problems that we work on, which are anywhere from a handful to like 20 exposures that are all continuous, I really haven't seen any methods that that sort of naturally extend to the context of mixtures. And then we'll just wrap up, and there'll probably be time for questions at the end if you have any, or we can all just take a breath and go home early. So far, our textbook examples have only included a single binary exposure, big A. Mixtures, for the most part, every context that I've seen have continuous and potentially high dimensional exposures. This was actually meant to say highly correlated exposures, but both of those things matter here. So we've got potentially high dimensional exposures. They may be highly correlated. And because of either the high dimensionality or the correlation or both, we're going to run into issues of sparsity, where there's going to be certain ranges of exposures that are just not observed for different covariate or exposure strata. And again, this is not necessarily something where we think it's impossible, so we may not be worried about positivity per se, but sparsity, which is something we've known about for a long time, is still an issue and it's still a challenge for causal inferences. So taking our example, a mixture of multiple exposures, arsenic, beryllium, and cadmium, all continuous, means we can't rely on any of the concepts that I've raised right now, at least in terms of the literal way in which I presented them. So we'll get into why. So just wanting you to recall our simulated example, we've got 3 exposures. We've got an outcome, mental development index. This is why sometimes it just shows up as MDI because that's not too onerous. And then 2 potential confounders. And, you could think of proximity to the coal-fired power plant. You could think of this as sort of the like primal confounder, and that if we adjusted for this, we would eliminate confounding by urbanicity and black race. But for the most part, I'm going to just consider this as being something that's unmeasured. So we'll say that we can't adjust for this. It doesn't really change things if we do have this thing measured, but it's always important to think of, in my opinion, it's important to think of sources of exposure when thinking about your confounding pathways in the context of mixtures. So there are going to be, other sources for each of these things that may have other confounding pathways. But for the most part, you can just think of this thing being unmeasured. So in order to control confounding, we need to block these potential pathways or potential colliders as we need to adjust for these things or be careful about adjusting for these things in the case of race. So just as I'm realizing here, this should be there should be a direct arrow here. There's going to be potentially collider bias here, but I'm not trying to trick you with collider bias. So I am going to fix that on the GitHub site, but this is not intended to trick you with a collider thrown into the model. So basics of this data set, again, there are 2020 individuals. The first 5 observations look like this. So we've got urbanicity, self-reported Black race as both being binary variables, and arsenic, beryllium, and cadmium all being continuous, as well as MDI being continuous. We've got highly correlated exposures, so Pearson correlation coefficients of at least 0.68, if not higher. One thing to note here, and this is something that comes up often when looking at disparities, and it's not something that there's really, in my opinion, a satisfactory way to deal with an analysis, is that you see exposures being much higher in populations that have been subjected to things like redlining, or there's other historical forces in place where we've got certain populations of interest that are just exposed to higher levels of things. Even given something like the fact that they're probably more likely to live towards urban centers, the Black participants in this study, even given the urbanicity variable, are going to be more likely to be exposed. And this is something that comes up often, and I'll give you some tools of how to think about this in terms of effect measure modification that actually account for the differences in exposure, and we don't sort of have to discuss those differently. The outcome looks sort of roughly normally distributed. So we can get away with a linear model. That's really not the way you pick a linear, choose a linear model with normal errors, but we're going to go ahead and say that this is going to give us approximately normal errors, so we can use a linear regression model in order to make inference if we need to. So under our DAG, for a single exposure, and we'll just say arsenic, the minimal causal unit that we need is this thing. So again, I referred to this as like a conditional effect earlier, even though it's not really an effect. That's Udea Pearl's term. But it's this idea that we need the expected outcome given our exposures and all potential confounders of that exposure. Now, according to our DAG, if we adjust for our measured confounders, urbanicity and Black race, we don't necessarily need to adjust for these. But if we have other sources of exposure, then we would definitely need to adjust for these. And I think as kind of a default analysis with mixtures, we often think about including these other exposures in the model to deal with things like co-pollutant confounding. So even though it's not strictly necessary with our DAG to adjust for these to estimate an effective arsenic, I'm including them here. So I'll call this the minimal causal unit, meaning we need something like a regression model where MDI is our outcome, we include all our exposures, and we include all the confounders. So roughly, in order to identify a causal effect, thinking back to sparsity, we'd need to observe roughly that all values of, if we're thinking about estimating an exposure response, I should say, of arsenic, where we're looking at the change in MDI for a 1 unit change in arsenic holding everything else constant, we would need to observe at all those other constant values variation in arsenic of about 1 unit. And this is really like messy language, so it's kind of confusing, but this is pulling directly from our sort of discrete world that we've had before. So the actual definition of something like sparsity or non-positivity in this continuous setting actually involves a lot of higher level math that I don't even understand. But we can think of this as an approximation to this continuous world, given what we already know about discrete data. And I'll give you an example of this. So it's not, we don't need to rely on just my poor interpretation here. So just visually, we can see whether or not sparsity is going to be an issue. spoiler alert, like sparsity is always an issue in mixtures data. We've known this for a really long time. Lots of people have written things about it. My favorite paper on this is from John Snowden. But the basic idea is with mixtures data, we often have correlated exposures where if we did a scatter plot, it's never going to look like this in real data because like we'll have, really ugly measurements somewhere. But in sort of this ideal data where we don't have that problem, we see this idea of correlation between these two things leading to a positive trend if we were to fit a trend line here. So I'll orient you to this a little bit. So recall that we're thinking about estimating an independent effect of arsenic exposure. And that independent effect, we'll say it comes from a regression model, but we're thinking about a 1 unit change in arsenic. And here, somewhat arbitrarily, I've chosen 1 unit change in terms of a policy difference where we're changing from 1.5 units of arsenic to 2.5 units of arsenic. And we're holding this constant at a specific value of beryllium. Now, for this example, if we were adjusting for all those other things, we're also holding those other things constant. So this isn't an exact representation of all the data, but if these were the only two exposures that we had, and these were sufficient for controlling confounding for each other, this would represent a true causal consideration in this very simple diagram. But if we can show that this is a problem even in this very simple setting, once we start introducing more variables, that's going to mean it's even a bigger problem. So what we're interested in, and it's not shown on the plot here, so don't think of this as a regression line, but we'd be interested in estimating the mental development index in these individuals where they've got arsenic exposure of about 0.5. Sorry, that should say 0.5 to 1.5. So about 0.5, and we also want to know the MDI of the individuals at around 2.5. Now, if exposure were randomized, we could just take that average, the average MDI in these people minus the average MDI in these people. And when I say people, I mean just these little dots. So the MDI that corresponds to the individuals given at these little dots. And if exposure were randomized, that would be our causal effect. Because beryllium we think of as being a confounder of arsenic, what we would need to see is that conditional on different values of beryllium, we would be sort of contrasting folks at the left end of the line versus folks at the right end of the line at different values of beryllium. And we would be kind of averaging over those. So we can think of identification here as roughly, there are some points sitting under this end of the line, and there's some points sitting under this end of the line. It's not an exact mathematical statement, but I think it gives you the right idea about what identification means in the mixtures context. So we've, on the previous slide, we fixed beryllium at 1, and we had identification. There were sort of points sitting under either side of the line. But if we fix beryllium at a different value, and this is a value of beryllium that we actually observe, but what we don't observe is lower values of arsenic in sort of this, neighborhood of beryllium, what we would call, if beryllium were binaries, we would call the stratum of beryllium, but we'll just call this a sort of a neighborhood. And what this represents here, if we were fitting a model, would be model extrapolation. So we're making inferences about individuals for whom we have 0 data at all. It would be people with arsenic exposure around 0.5 and beryllium exposure of 0.3. So this may be possible, but it's just not observed in our data. So we're violating sparsity in that case. This issue is well described. Again, this is sort of a fundamental piece of mixtures, maybe just stated in a different way. And it seems hopeless that we'll be biased because this is a really basic thing, just looking for a 1 unit change in arsenic, at a couple key values of the other exposure. And we can't even do this in a model that has 2 exposures. So this, and these are highly correlated, but the problem is going to grow with more exposures, but this makes this entire endeavor seem kind of hopeless. We'll note that a 1 unit change in arsenic is observed when beryllium is equal to 3.0. It's just not the original change in arsenic. It's a 1 unit change in arsenic up here. So we can make something of that. So if we can assume that the rate of change in the outcome per unit change in arsenic is roughly the same down here and up here as it would be over here, what we can say is that we've gone from non-parametric identification to parametric identification. So the act of fitting a model that allows us to extrapolate still gives us causal inferences. Now, I don't want to overemphasize the utility of this because this is a fairly dangerous concept. And even in these simple data, we can see how extrapolation is going to occur. But this is possible. And so with methods like g-computation, which I'll discuss later, in the mixtures context, we can think of as substituting our sparsity assumption for a parametric modeling assumption. What this means is that we have to get the parametric model right within the bounds of the place in which we're extrapolating. So it would essentially be, anywhere on this plot, we would have to assume that our model is just as correct out here as it is in here. And this is a super dangerous assumption. It's never going to be met. The old adage, all models are wrong, some are useful. It can be dangerous to do this extrapolation because we know our models are going to be wrong. This is sort of the realm of a lot of what machine learning is doing now is figuring out ways to get accurate models, both for the data and outside of the data. But this is not something that should just be generally done without really thinking. So this sort of makes it the endeavor a little bit questionable, but provided that you understand the shortcomings of taking this particular approach, provided that you know that there is extrapolation going on, you can at the very least contextualize the results from fitting a regression model in mixtures data where you have to adjust for other exposures. So the amount of extrapolation that's going to happen, it turns out we don't actually have good intuition, and we can't build intuition from these simple plots into what happens in higher dimensions. So, once we get past a few different exposures being in the model, these data get really, really sparse. One way that this is sometimes expressed is that your sample size need grows exponentially with the number of dimensions that you have. So it's not just that you would need to take your sample size and add 100 individuals and then you could throw in 5 new variables. It's really that the more and more things you add to your model, your data needs become so great that you eventually need a sample size that's the population size of the Earth. This is a little bit inexact, but this is what's known as the curse of dimensionality, that this extrapolation gets really bad really quickly as we add more and more exposures to the model. So partly this is just to serve as an additional caution when using these approaches that rely on accurate extrapolation. I call the curse of dimensionality part of the fundamental problem of mixtures. And this is my term, so you don't feel like you need to use it or that there's a citation for it. But it's a thing. But the fundamental problem of mixtures is the correlation between components of a mixture means that we should suspect copollutant confounding. So we always, if we're thinking about causal inference, we want to adjust for those other things. But adjusting for that confounding in statistical models leads to problems on its own. So really this fundamental problem of mixtures is a catch-22. We've known about this problem for a long time. We're just finding new ways to describe it. But really this is a problem of information. So it's a problem of sparse data. And we're not going to fix the curse of dimensionality through any of these tricks, but we can at least make some of them better. And I'll talk about the things that I'm not going to show you first, but just to raise this idea that, one way to get around the curse of dimensionality is to reduce your dimension. So taking 30 exposures, reducing them to just a few, using something like PCA or clustering or profile regression. Then sort of the Bayesian or machine learning way, alternative machine learning way, regularized machine learning way, would be doing shrinkage, model selection, or using Bayesian priors. And you can think of selection again as sort of dimension reduction, but it's happening within the model rather than outside of your statistical model. And then shrinkage and Bayesian priors, you can think of these as roughly the same thing, but really it's just a way of taking these somewhat overfit models and kind of dialing down the overfit a little bit to produce more reasonable estimates that often win in terms of things like mean squared error, if not bias. So these are sort of traditional ways to address sparsity in data that we take advantage of a lot in mixtures, and really that's why is this fundamental problem of mixtures. There's another approach that I sort of advocate, and it's maybe changing the question isn't the right way to state it, but thinking differently about mixtures in terms of the type of question that you really can feasibly ask. And so there are a few methods that have been kind of designed to specifically with mixtures in mind: weighted quantile sums, Bayesian kernel machine regression, quantile g-computation, and these all sort of involve, in one way or another, changing this question, going from this idea of estimating an independent effect of a single exposure conditional on every other exposure, going from that sort of messy, tricky setting to estimating something that's maybe a little more feasible. And so this is red here because this is really what I'm going to talk about for the rest of our time. So just introducing this idea a little bit, we're revisiting the other problems. So one problem is we've got continuous exposures. The other problem of mixtures is that we've got multiple exposures. So sparsity is going to happen regardless of whether or not we have other continuous exposures that we're interested in, because we're going to have other confounders that we're going to need to stratify. So sparsity is a problem regardless of whether or not we have a mixture, simply for the fact that we've got continuous exposures that we may not observe everywhere. Textbook examples rarely mention more than one exposure. So this is sort of tricky in terms of thinking about how we might want to apply causal inference concepts to mixtures. Notably, the fundamental problem of mixtures really describes problems with estimating the effect of one exposure holding others constant. And I've just noted this down here as, again, harking back to our conditional exchangeability and sort of our minimal causal unit. This is kind of the thing that we're estimating by comparing individuals at either side of this line. So this is sort of our causal estimate put in terms of a policy contrast. We can think of another way to do this, which is thinking less about horizontal or vertical lines and thinking on the diagonal. So we could consider the effect of two exposures where the contrast, again, is roughly the average outcomes over on the left side of the line versus the average outcomes on the right side of the line. But here, notice that we're changing both exposures simultaneously. And the way we would express this in terms of potential outcomes is now we're not conditioning on beryllium taking on a specific value over here, but we're considering it part of our policy. So we're saying, what is the effect of increasing A and B by 1 unit? And this is, here 1 unit refers to 1 observed quartile. So if we increased arsenic and beryllium by 1 quartile from the minimum to the 25th percentile, this would be the contrast that we would make. And the thing to notice here is that we, sort of right off the bat, there are a lot of data under both of these points. So that's the first thing to notice. We're, at least for this very local causal contrast, we're very well identified. Now we could think of moving up one level of exposure. So we did this before with just arsenic, where we went from 0.5 to 1.5 to 1.5 to 2.5. Now we're thinking of both of these exposures being equal to the sort of second quartile, or this would be the median, versus the 25th percentile. And that's a causal contrast is expressed down here, as we're comparing outcomes at this joint value of exposures versus this potential outcome at a smaller joint value of exposures. And again, this is moving along the diagonal of the plot. So we've identified another region where, at least graphically, we look really well identified. We can keep going up the plot. So the third quartile versus the median. And this is actually getting to something that's maybe a little more familiar in the epidemiologic literature, and that's thinking about joint effects. And actually the best place I've seen this expressed is in something that really doesn't have much to do with joint effects, but it's this paper by Tyler Vanderweel where he defines joint effects in terms of potential outcomes where you've got two exposures up here rather than just one. So this we could call a textbook example. It's maybe not one we see very often, but we've got something that is maybe better identified as the joint effect. And again, we're not conditioning on observing values of beryllium out here or observing arsenic values down here. We really are conditioning on both of these being increased simultaneously along this diagonal axis. And even this very last quantile, so this is the maximum of both exposures, and we're getting into a sparse scenario out here, but we're still really well identified here. We haven't identified a single region where, we think we're really poorly identified, where there are no data at all in that region to inform our effect estimate. So, just really quickly, like leafing through 4 of these different ways of expressing a 1 quantile increase, we can see that the joint effect is actually better identified in correlated exposure data than the independent effect. So this is, sort of thinking about this like a line by line where, we're thinking of people with exposures down here versus people with exposures right here versus people with exposures right here, and so on. This is sort of like turning our variables into turning our continuous exposures into indicator variables. And this is actually a strategy taken by weighted quantile sums and quantile g-computation, is sort of chunking up this line so that we can fit a regression line along along a line that's the joint increase in quantiles in 2 or more exposures. So now if we think about bringing our outcome into the equation. So here we've got our expected value of MDI, and this is the joint quartile of arsenic and beryllium. Now this is the actual, sort of dose response from our data. If we actually did the indicator variable version of this, and we just estimated the mean MDI at each of these, and this shows up in the code, so you should be able to see this when you actually look at the code. This tells us that we've got, something that's kind of nonlinear in the joint exposures. And really, this is just to remind you that we haven't even seen the outcome on any of these plots yet. So what we're looking at here is, as we're moving up here, that's like we were moving up the diagonal in the previous scatter plot of those 2 exposures. So if our causal identifications are, was that a question? If causal identification conditions are met, where we could substitute our rough, we'll call this a model, even though it's not really, in for positivity or sparsity, then this can be interpreted as a regression line for a marginal structural model. So if you've ever heard this term only a few times, you probably heard it in respect to inverse probability weighting. But a marginal structural model really is just a model for the potential outcomes. And inverse probability weighting is one way to fit that model, or one way to estimate the parameters of that model. But the marginal structural model itself really just refers to a model for the potential outcomes given exposure. And here that just is a model for the outcome given the joint quantiles of exposure. So methods like Bayesian kernel machine regression and quantile g-computation can give estimates from a marginal structural model. Bayesian kernel machine regression, that's, I don't think it's the default, but you can get there. There are some approximations that go in to make this faster. So you could think of it as an approximate marginal structural model. If you're looking at joint effects of increasing every exposure by a single quantile. Quantile g-computation is sort of targeted towards this, but giving estimates from a marginal structural model. So here's just a linear fit, which I'm not advocating as being a good fit, but this would be sort of the default quantile g-computation fit, where we just draw a line down this. That doesn't seem to be a very good fit. So we could fit a polynomial curve in quantile g-computation that fits these a little better. So this is just what quantile g-computation, Bayesian kernel machine regression to some extent, and even under some conditions, weighted quantile sums, what that particular model is estimating is it's fitting a marginal structural model for some outcome, given that we're doing joint increases of all the exposure at once. And this is, this is, I think, well described in the literature, but this is just a different way to think of effects that we can already get justified in a way such that we're reducing some of the inherent problems of mixtures in terms of sparsity. So we've got something that we may actually think be a little better identified than just an independent effect of either exposure. This actually plays out in simulated data, and I've seen this in a couple different settings. So to orient you to the plot, this is from a simulation that came up in the original quantile g-computation paper, and this is thinking about an independent effect of a single exposure, so x1, versus the joint effect of two exposures. So this is the marginal structural model parameter. And this would be the parameter from a linear model where we've done the same variable transformations that we've done to get quantile g-computation to work. So we've quantized things. But what you can see is on the y-axis, we've got confidence intervals. So this we can think of as estimate of precision. So as we go up, our precision gets worse. Our confidence intervals get wider. As we go down the y-axis, precision improves. And there's this, I found it to be surprising at first, but it now sort of makes sense. But there's this interesting phenomenon with joint effects where as exposure correlation goes up, your precision for your joint effect actually improves. Whereas here's sort of the classical problem of mixtures where an independent effect, the precision just eventually blows up as your correlation gets larger and larger between your variables. So correlation is a problem in this case. This is another way of restating the sparsity problem. Correlation between variables is a real problem because you end up extrapolating and you're making inferences in data that you don't have using independent effects of exposure. But for joint effects of exposure, you tend to be well identified, and you're even better identified at high correlation because as variables become more and more correlated, the joint effect really becomes like the effect of one variable. So in some ways, you're reducing the dimension of the problem by focusing on the joint effect. So you can sort of recast this to some of the other solutions that we've had for mixtures data in the past. But this gives us some hope for estimating joint effects even at high exposure correlation. But thinking in terms of identifying bad actors, really this is what our interdependent effects are. that becomes a little more suspect. Obviously, there's different ways to think of bad actor identification in terms of picking out one exposure that seems to be worse than everybody else. But in terms of effect estimation, as correlation grows, trying to identify a bad actor becomes really suspect, whereas identifying or estimating joint effects does not to the same extent. So spend a little bit of time just discussing some of the methods that are, at least have been raised as potential ways to take sort of these understandings of sparsity and how we might sort of get around that, and actually estimate things that are respectful of the fact that we have sparsity, and because they're coming from the field of causal inference, also allow us to ask really interesting questions that may go beyond just a single exposure response parameter that, again, it's not something your grandparents can interpret. So you sort of have to fudge your results in order to express it to a layperson. Whereas with causal inference, if you believe your assumptions, you can create really clear causal contrasts that are just as easy to state to a statistician as they are to your grandparents. So inverse probability of weighting of specifically inverse probability of exposure weighting is a method for fitting marginal structural models or estimating other policy effects that are akin to how would the average outcome change if we reduced everyone's exposure to zero. So marginal structural models is where they're often used, but we also see that in terms of estimating these, sort of yes or no policy effects, or contrasts of two different exposure settings, and thinking about sort of a binary comparison rather than a regression line. So IPW within the mixtures context would rely on having a regression model for each exposure of interest. So if we've got 3 exposures in the example I'm using here, we'd have to have 3 different exposure models. And each of those models would be conditioned on confounders and co-exposures. And then we'd also need an outcome model or a set of individuals who represent the policy contrast of interest. And I say representative of this policy contrast of interest because really what IPW is doing is taking these individuals who represent this contrast of interest and weighting them up so that these people can represent the entire population. So now we've taken individuals with specific values of, in our example, would be Black race and urbanicity. We would weight them up such that they represent the distribution of Black race and urbanicity in the population, had exposures been randomized. And this is the key for inverse probability weighting, is we're creating a new population where if exposure is effectively randomized. And so we can either fit a marginal structural model or we can do some basic comparisons. The complication, another complication for mixtures is that we have continuous exposures again. Methods for weighting with a single continuous exposure are fairly well known, but I've only ever seen them work in fairly simple examples. I think there's maybe a couple compelling examples out there, but really you just don't see this type of analysis very much, and I think for good reason. While I was a graduate student, I spent a pretty substantial amount of time trying to do this exact thing, and it just, it seemed hopeless in data with any sort of complications to it. So IPW with continuous exposures is extremely tricky. And then, again, for joint effects, we'd need a model for each exposure of interest. So now we've got these tricky models, but we need not just one, but several of them. So for this, this will be the last I mention IPW, hopefully for a long time. For mixtures, it seems like it's sort of non-ideal for mixtures contexts, except in very, very specific circumstances where maybe you've got a small mixture, you don't have continuous variables, and you really are interested in a joint effect, and maybe you've got a lot of data. But otherwise, you run into a lot of problems using IPW for the types of data that really typify mixtures. G-computation is the second approach I mentioned. This is a generalization of standardization. So there's nothing magical about g-computation. This would involve concepts that you learned in EPI 101, where we're taking an estimate and we're standardizing, we're taking a stratum specific estimate and then we're standardizing that to a specific population. G-computation is a way to extend that concept to, things like continuous exposures, continuous confounders, exposures that vary over time. But it's still built on this nicely interpretable framework of standardization. G-computation can be used for fitting marginal structural models or estimating these policy effects, and I'll give you examples of that. For time-fixed exposures, G-computation only requires a single standard regression model. So unlike IPW, where we needed a model for every exposure, with G-computation, we only need one. Quantile G-computation, I won't say much about it, but it's a special case of G-computation in general that fits a marginal structural model under a fairly constrained underlying model. But G-computation more generally is an extremely flexible approach where you can answer a lot of cool questions. If you extend it to time varying exposures, it requires more modeling. I've cited one of my own papers here. I didn't come up with the method, but I certainly understand this paper better than the others. So if you want to follow up on time varying exposures, I would start there. And then you can ask me questions if you're confused. But G-computation, as I said, with time fixed exposures is fairly easy or straightforward. So if we're using the coal plant data, the first step of G-computation is just to fit a regression model. So we've got expected value of our outcome given arsenic, beryllium, cadmium, and then we've got black race and urbanicity. And this again, going back to the original description of the data where MDI had this nice normal distribution, that's not sufficient for choosing a linear model, but gives us some hint that we could start with a linear model. So what I did was fit a linear regression model given all these things, and I'll show you what that model looked like. The second step of G-computation is to take that model and just make predictions from that model under policy levels of exposure. And this is where G-computation really shines, is in these simple contrasts of policies where you're setting exposure to be specific values. Quantile G-computation again gives you exposure response or dose response parameter, but G-computation, it's sort of really easy to get these nice policy contrasts. Then the last thing we do is we contrast the average predictions for the population or subgroup. So we would just do this, we would make predictions under multiple different policies, and then we would calculate effect measures by addition, subtraction, or division of those particular effect measures. Actually, we would not use addition, we would use subtraction or division. So this is just referencing the R code that is available at the GitHub link that went out earlier. Again, you can just go to my GitHub page, searchable in Google, you can find the code. But this is kind of a relatively strange model if you are used to interpreting model coefficients. So what I've done is include all of the exposures by themselves. And this is sort of a feature of R, is that if you include this product term, it gives you both of the main effects as well as the product term between these. So you can think of this as a shortcut if you're not familiar with R to doing a model with 3 terms in it. And then I do that for each of the exposures. So there's product terms for all of the exposures and both of the potential confounders, as well as product terms between the exposures. Now, I am not going to make claims to the accuracy or veracity of this model. This is mostly done for didactic purposes to show you that we can fit these kind of bespoke and uninterpretable models and still get nice inference out of it. So the second step is to make predictions from that model. And one thing you could do is set all exposures equal to 1.0 and make predictions. What I did here was set all exposures to be the median exposure in the original data set. and then just make predictions under those new data. So fit a model in the original data. I created some new data in which I want to make predictions. So that's people with different exposures. So this again is, you can think of this as like a counterfactual world. And then I make predictions in this counterfactual world. And the predictions are going to look something like this. So here's our original data set, and I've just tagged on the predictions. And we've got, sorry, I have the original outcome, not the original exposures. These are the policy level exposures for this particular data set. And so you can see these are all equal to the median. We make predictions. And this is just the basic form of g-computation. There's not a whole lot more that goes into it, because all we do is we take means of the predictions, and I can compare those to the value in the data set. So the mean under this, this policy or this intervention gives us a predicted MDI or average MDI of 97.7 versus the original data, which is 96.9. So if we could feasibly carry out this intervention to expose everybody to the median, which is, you know, this is just an example. I'm not saying it's realistic or useful, but that would mean we would improve MDI in the population on average by 0.8 units. We can change this to look at subgroups. So using our original model again, we can just make predictions among the Black individuals in the data. And now we get an estimate of 1.8. So this is larger than our other estimate, which was less than 1. So ignoring uncertainty, we can see that the effect of changing exposure is going to be larger among the Black participants. And this sort of is in line with what we saw with the exposure distribution among Black participants. So the way to interpret this is that if our causal identification conditions hold and the linear model that we fit is correct, then causal inference, or the sort of theory underlying causal inference, licenses us to interpret our results causally. This should not be the default. The hard work of causal inference is in showing the identification conditions hold at least approximately. However, even if those assumptions don't hold, g-computation still is of value. It's still as valid as you know, any other regression model that we fit that we don't think meets the causal assumptions. Here it just gives us a standardized effect estimate. And it has the advantage of still targeting our scientific question of interest, even if we may not meet all the assumptions. So it's still answering the question we want to ask. It's just that we know it may be biased due to not meeting the causal assumptions. So just to kind of drive home this point, this is the underlying, what I'm calling the underlying model of g-computation. So this is step one of g-computation, is to fit this sort of highly stratified model. You know, just looking at p-values, you know, you might be tempted to not include anything in this model. That's not what I would use the p-values for, but certainly there's not strong statistical evidence for, you know, either main effects or effect measure modification. You know, we see some large coefficients, but, you know, because of the rather large standard errors, it's not clear that we should really believe those. The product terms are going to be difficult to interpret because, you know, we've got multiple product terms, and so it's not a simple effect measure modification problem in the way that we would usually use product terms. So we've taken this really complex model and we boiled it down to relatively simple causal contrast. So we can do something more interesting. So the more interesting things are getting back to this idea of an attributable difference. So what if we could set one of the exposures to 0? This is, we're reintroducing our idea of you know, the fundamental problem of causal inference in mixtures, fundamental problem of mixtures, which is, you know, we're estimating something that we think is probably not well identified. But again, at the very least, this is targeting something we're interested in. So it's the effect of taking everyone who's exposed to arsenic and setting their exposure to 0. And then we could think of more realistic settings, such as coal plant decommissioning. So I'm working on the assumption that if we decommission the local coal-fired power plant it would decrease arsenic by 96%, beryllium by 91%, cadmium by 50%. These are actually informed by the National Emissions Inventory data, but you can consider these sort of arbitrary here. And then we can do this restricted to Black participants only. So again, thinking about issues that come up with inequities and exposure. So if we estimate this among everyone, the asterisk here is not for a p-value, but just to show you that the confidence intervals were given by bootstrapping, which is, you can see that in the code. And so you see these sort of attributable mean differences. Arsenic, has the largest effect among everyone, among Black participants and among non-Black participants. Beryllium really seems to have opposite effects, but there's a lot of uncertainty there, so it's hard to make much of that. Same thing with cadmium, where there's a lot of uncertainty relative to the effect size. However, this joint effect of a shutdown of the coal-fired power plant, we can see fairly marked changes in MDI, or at least the simulated MDI, where we see a much larger effect among Black participants in the study, even though we didn't see any statistical evidence in the underlying model that there's real effect measure modification on that sort of additive scale. Even without that, almost, well, it's hard to say how much, but probably predominantly due to exposure differences between Black and non-Black participants, we see a much larger effect of this particular causal estimand, expressed by this particular causal estimand in the Black participants versus the non-Black participants. So this is what I meant before when I said, we can incorporate measures of exposure in our way of thinking about effect measure modification that don't come up in sort of standard regression analyses. These specifically incorporate ideas of inequities in exposure. So under the causal identification conditions, correct model specification, eliminating arsenic would result in a 2.8 gain in the population average MDI. That effect would be stronger among Black participants. Provided that we've accurately predicted what would happen to these exposures if local coal-fired power plants were shut down. So you could think of this as sort of another assumption where we're mapping on, how we're actually manipulating exposures versus how it would actually happen in the real world. Black participants would have experienced a nearly 6-point gain in MDI, and that would have been a much larger gain than the white participants. Notably, the underlying model had weak evidence for this effect measure modification that we saw on this more marginal scale. I attributed that to differences in exposure between the two groups. So I'll just go through this real quickly because it's, I've been talking at you for almost 2 hours. My voice is going, and I'd rather get to any questions that you have. But quantile g-computation is this method proposed specifically for mixtures. It's available in the QGComp R package. And what this does is estimates a marginal structural model for a 1 quantile increase in exposure. And again, the benefit of this over the sort of standard g-computation that I just showed you was really thinking again about what is identified in mixtures. And so this identifies an effect where, again, we're sort of going up the diagonal of that scatter plot of exposures. So these joint effects where we're going by quantiles of observed exposure tend to be really identified, at the expense of some interpretability. So this doesn't give us the nice policy estimates, but nonetheless, it takes advantage of joint effects in a way that regular g-computation isn't necessarily guaranteed to. So here we see sort of, it's similar qualitatively, and the distinction here between the negative signs of our effect measures and the positive signs that we saw before is that this dose response is estimating the effect of increasing exposure, whereas the previous sort of exposure policy contrasts were really comparing the effect, or it was really estimating effect of decreasing exposure. So implementing a policy that decreased exposure. So these give the same interpretation, even if they're on opposite sides of the null. But again, you see among Black participants, this joint dose response being larger than it is among the non-Black participants. And generally just stronger evidence among the Black participants that the exposure is harmful, or the joint exposure is harmful. So again, the real hard work is always in the assumptions. Just take care. You know, this is a really artificial example in some sense. Like, we've relaxed some of the pieces of our textbook examples, but we still don't have to deal with things like selection bias or, you know, small sample sizes. We had a sample size of 2,000. So in some of those more complex scenarios, we may have additional modeling problems that require Bayesian solutions, or we might think of machine learning, regularized machine learning. There are a couple of papers here that you could follow up with about those things. And there are still a lot of technical issues to address in inference in high dimensions. I don't want anyone to come away with the impression that this is really a solved problem, or you know, some people think it's sort of unsolvable. Really, we're in an area where there's no data for a lot of different questions. And so there's a lot of you know, really technical issues to iron out. But you know, I think g-computation, and specifically in causal inference in general, can really do a great job in informing mixtures in terms of giving us things that are really interpretable, even though we've got really complex data. And even if we don't believe the causal identification conditions fully, methods like g-computation are, you know, they're still as valid as any standard regression approach. They're really helpful for taking complex models where we think we've got, you know, product terms, nonlinearities, and it still gives us interpretable results. Done carefully, focusing on joint effects can reduce some of the identification conditions that rise, or issues that arise in mixtures, the sparsity issue. And lastly, g-computation allows us to sort of trail off the end of this page, but really g-computation allows so much because, you know, if you think about the policy interests or policy effects that you could be interested in, you know, that's a potentially infinite set of different ways you could look at exposure other than just an exposure response, all coming out of the same model. So really g-computation allows us to do, it gives us a blank slate in terms of the things we can do. But again, just take care when applying the causal assumptions. So thank you all for, at the very least, being present. And I will take questions. You can also follow up with me on email, and I will, I'll actually flash that GitHub link again in case you missed it the first time around. But I will stop talking now.
Thank you, Alex. Does anyone, we had no questions in the chat while you were presenting. Does anyone have any questions or comments or discussion points?
And it has been a long couple of days, so, you know, everybody take a breath.
We will be posting this presentation on ISEE Global's Education YouTube channel. So you have the opportunity to watch it again, and feel free afterwards to email Alex if you have follow-up questions. This was great, Alex. I enjoyed it a lot. Thanks.
Great. Thanks.
Okay. Thank you, everybody, for joining. As Alex said, this has been a very tough couple of days. So thank you for being here. We appreciate it. And we hope to see you all very soon. Thank you.
Bye all. Take care.
Bye.